Hello, here we are with section 7.3, where we're looking at applications of logarithms to modeling real life problems. We're using mostly the same methods as in 7.2, with a few more complications. So, involving things like half-life and doubling time and some other stuff. So, anyways, let's look at example 1 here. We want to see when will a bank account that starts with $5,000 and earns 3.5% per year reach $10,000. So, let's see. Uh, so first of all, let's start by writing a formula for the balance. Maybe we can call it B. So B of t should be a function that gives you the bank account balance, and it started at $5,000, so that's going to be the initial value, and then it earns 3.5% per year. So I'm going to write this in the form 1 plus r, where r is the interest rate, which when you convert that to a decimal becomes 0.035, and then all of that to the power t is going to give you a function where the output starts at 5,000 when t is 0, and every time t goes up by 1, it increases by 3.5%. Okay, so now that will get us started with this, but we want to know when. That means what is t that makes it so the B of t is $10,000. So I'm going to replace the B of t over here with $10,000, like so. That should be equal to 5,000 times 1.035 to the power t. And then we're going to solve this just like we did with the other equations in 7.2. So first we want to get the exponential part, the 1.035 to the power t by itself. So we're going to cancel out the 5,000 by dividing both sides by 5,000, which will leave you with 2 equals 1.035 to the power t. Here's where you want to take a logarithm of both sides. We're going to do log of 2, and then also log of 1.035 to the power t. And then you can use the log law that says a logarithm of something to an exponent power, you can take that exponent down and write it as multiplication here. So this will become t times log of 1.035, and on the other side you just have log of 2, and you can cancel out this multiplication by dividing by log of 1.035, that number that's getting multiplied here. We'll cancel that out, doing that on both sides. And this will leave you with t is approximately this thing, log of 2 divided by log of 1.035. And we can do that with a calculator here. And we're getting 20.15 out. And that's how many years it takes to reach $10,000. Okay, so that sounds good. You could always check this result by plugging it back into the original equation. If we do 5,000 times 1.035 to the power 20.15, we're going to get, yeah, about $10,000 and 41 cents because we rounded off a little bit. Okay, so let's look at B here. We want to write the formula for the bank account balance in this form. B of t equals a times 2 to the power little t, the variable, divided by big T. And remember, this is the formula for doubling time. The doubling time is how long it takes for this exponent to go up by 1. So that's going to be whatever big T is here. And we can see here that the doubling time to go from 5,000 to 10,000 was 20.15 years. Well, then that's going to be the doubling time in general, because that's the way exponential functions work, that every time a certain amount of time goes by, like 20.15 years, the exponential function is going to get multiplied by the same amount, which in this case is it's getting multiplied by 2. So you could write this as B of t equals the starting amount, 5,000, times 2 to the power t divided by 20.15. And that's basically the answer. There's another way you could get this if you don't know how to figure out what this t should be. So I'm just using what I know about doubling time and exponential functions, but here's that was the first way, but here's another way. It's always good to have more than one way to solve a problem, because sometimes you forget one way or you need to check your answer. What we're trying to do is we're trying to make 2 times t divided by big T equal to 1.035 to the power t. And we got to figure out what big T is. We got to solve this for that denominator, because we need to know what that is to write this formula, right? So we're going to solve this for big T. And big T is part of the exponent of this, so it kind of makes sense to take a logarithm of both sides. Just like we did before to get the stuff you're trying to find out of that exponent. And then all the exponents come out. So with this one here, the exponent is t over big T. That fraction is getting multiplied by log of 2. And over here, it's just little t times log of 1.035. And this is an equation that we can now solve for big T. Now I see that there's a little t in both of these. You could multiply both sides by 1 over little t to cancel that out. And that will just leave you with 1 over big T times log of 2 equals log of 1.035, because the little t's canceled out. And then if you solve this equation, I'm running out of room here to do it, but if you multiply both sides by big T and divide both sides by log of 1.035, I'll sort of skip some of those steps because I'm out of room. You'll end up with log of 2 divided by log of 1.035 is equal to big T. And hey, log of 2 divided by log of 1.035, that's what we just did to find the 20.15 before. So that gives you t is approximately 20.15. And that is another way you can find that t. That's sort of the long way. Okay, so yeah, we're sort of looking at solving these equations, but trying to tie it all together with concepts like doubling time and half-life is what this section is sort of about. So for example 2, when you consume caffeine, your body removes about 11% of the caffeine each hour. Now, let's suppose you have a big cup of coffee with 200 milligrams of caffeine, and you want to find the half-life of the caffeine. So we're going to start by writing a formula for C of T, the amount of caffeine remaining after T hours. And then part B is what this question is really asking, just repeating it there. So to get the formula for C of T, that is going to be, let's see, it's starting at 200 milligrams after 0 hours. So that's going to be the starting amount that you put here, times, well, it's going up by 11% per hour, so it's going to be that times 1 plus 11%, written as a decimal, to the power t. Oh, but it's getting removed, so excuse me, that should be 1 minus 0.11. So in other words, this 1 minus 0.11 is going to be 200 times 0.89 to the power t. So in other words, every time 1 hour goes by, every time t increases by 1, the amount of caffeine in the body is 89% of what it was before. So if you have 89% remaining, then that's the same as losing 11% of the caffeine. Okay, so now we want to find the half-life of the caffeine. We got part A here, that's the answer. So B is the half-life. So the half-life is how long it takes to reduce by half. So if it started with 200, we want to know what is T, the amount of time, that makes this result become 100. So I'm going to take the output here, the C of T, and replace it with 100. And leaving the T as the variable. And if we want to solve this for T, you would divide both sides by 200 here, and you'd get 0.5, also known as 1/2, equals 0.89 to the power t. And here's where you can take log of both sides. Which gives you log of 0.5 is equal to t times log of 0.89, and then you can just divide both sides by log of 0.89 to get t here. Okay, and if somebody asks you the question in real life, like, how long does it take for half of the caffeine to leave your body, and you tell them the answer, well, it takes about log of 0.5 divided by log of 0.89 hours, then that's not really going to answer their question for them. They're going to not know what to do with that information. So we got to really finish the problem by getting this as a decimal so it has some real life meaning. And the result is about 5.948 hours, or you can call it 5.95 hours. Is the half-life. So that is part B. Let's look at part C. Repeat parts A and B, but this time, supposing you drink a cup of coffee with A milligrams of caffeine. So instead of getting whatever size cup of coffee that is. You had some other size, but we don't know how big it is. So for that, instead of using the 200 here, that's going to be A, just the variable A, whatever the starting amount is. So that this will look like C of t equals A times 0.89 to the power t. And now if we want to find the half-life is going to be the time it takes for the output of this function to become half of what it started. And it started at A. So it's a value of t, so that C of t is equal to half of A, or just A divided by 2 if you want to do that. So if we're trying to solve this equation, what is the t that makes it so C of t becomes half of A? That equation would look like this. And at this point, we want to solve this to find t. It's going to be the half-life that makes this equation true. You can divide both sides by A. And lo and behold, that is just going to cancel out. And you'll get 1/2 equals 0.89 to the power t. And 1/2, also known as 0.5 over here, we already solved this equation. Just like how we went from here to there, it's exactly the same equation. So I know the solution is going to be t is approximately 5.95 hours. So yeah, the moral of the story here is it doesn't matter how much coffee you drink, whether you have a tablespoon of coffee or a venti double shot red eye or something. The amount of time it takes for that to reduce by half is always going to be about 5.95 hours. So, and there's actually a lot of things in medicine that work, like drugs that sort of work like this, where the amount that your body can get rid of is sort of proportional to how much of the drug is in your body. And that ends up leading to an exponential situation like this. So a lot of drugs have a half-life, sort of like this. So, anyways, let's look at the balance of a bank account. It begins at $32,000 and earns 3.5% interest per year. When does it reach $70,000? Okay, so let's think. We know the starting amount is $32,000, and we know the interest per year. So to write the formula for this, it's just going to be the starting amount multiplied by 1 plus the percent growth rate to the power t. And if we want to make it reach 70,000, that's going to be what is the value of t that makes it so the result is 70,000. So you can divide both sides by 32,000. And 70 over 32. I don't want to round that off just yet. I guess I could reduce it a little bit. You could turn that into, let's see, 35 over 16 if you reduce that fraction. But I don't want to actually round it off yet, because the more you round off early in a problem and then do more arithmetic with that rounded off answer, the more rounded off your answer becomes, the less precise your answer becomes. So I'm going to leave it like that. and then take a logarithm of both sides, which is the usual trick to get the variable out of the exponent. And that's going to become the log law 3 says that you can take the exponent and write it out in front. And then to solve this for t, we can just divide both sides by this last log. All right, so we're going to do this on a calculator now. Log of 35/16 divided by log of 1.035, and you get 22.75 approximately. So yeah, that's about the number of years that it takes to get to 32,000. Oh, wait, no, it's 70,000, excuse me. Okay, so yeah, up next you got some exercises to do. Give those a shot. I'll show you the solutions in the next video so you can check your answers or get unstuck if you get stuck. See you then.